Hello class, welcome to another video in the Calculus 1 series. So we're going to look at Lesson 9, Basic Differentiation Rules. So in the previous lesson we looked at the introduction to the derivative and we used the two definitions for the derivative, the standard definition, the limit definition, and then we used the alternative definition. So this time we're going to look at some shortcut rules. So let's take a quick note on what we talked about in the previous lesson. So the definition of the derivative that we gave was the limit definition. So these are both limit definitions. So the first definition is based off of what's known as the difference quotient, okay? And the second alternative definition is one that you would use if you want to plug in a specific value of the derivative. So if you want to find a specific value of the slope. So here you can see that the symbol for the derivative is usually f prime, right? The little, if you see that there, another symbol is this dy dx, right? So this is the derivative of y with respect to x. And we can see that this here is my difference quotient. Okay, the difference quotient is essentially change in y over change in x. It's the slope. So it's the, and so if you take the limit of that slope, you get your derivative. So the derivative is a specific type of slope. Now the alternative definition is when you take this, you find the derivative and you plug in a specific value into the derivative. So if I wanted to define the derivative at a specific value, say at x equals 1, and then the alternative definition is good for that. However, it can only be evaluated at that specific point, whereas the first definition you can evaluate at any point once you find the derivative. So you have to find a derivative function first, and then you can plug in a value into it. So again, this here is the change in y over change in x, right? So we know that the derivative is the slope of the tangent line, which is the dy dx here. So this is the slope of the tangent line. And this here is the slope of the secant line, the traditional change in y over change in x. So if we're given a graph, right, and I want to find the slope of the secant line, well, I have to be given 2 points to find the slope, right? So I need, the slope of the secant line is known as the average rate of change. So I need to find 2 points. So let's say A and B, and then I need to figure out what the slope is, rise or run, from one to the other. So this is the change in y over change in x, okay? And that gives me my average rate of change, or the slope of the secant line. Now, if I take the limit as x approaches 0, well, that makes this approach 0. And so that makes this gets smaller and smaller. The only way for that to happen is for this point right here to get smaller and smaller until this point goes to this point right here. And then you can get the slope of the tangent line, right? That's not a very good tangent line, but you get the idea. This slope of this tangent line right here, and this is the derivative, the slope of that tangent line right there. It's really hard to tell, so let me erase everything else and kind of draw that again, just to kind of for you to kind of see. So if we got this curve, then if I wanted to find the slope of that specific point, that is my tangent line. And if I find the slope of this using rise over run, that is my dy dx, okay? So hopefully that makes sense. But that's what we had talked about in the previous lesson. So again, just to remind you, the f with the little apostrophe is read as f prime of x, okay? And that's the derivative of f of x, okay? So that's f prime of x, dy dx. Sometimes I'll just say it as dy dx, or I'll say dy over dx. Usually, if you were to actually say it, it's the derivative of y with respect to x, okay? So that's how you would say that. And then as a verb, when we say take the derivative of something, you could say that. You could say take the derivative of the function, or you could say differentiate the function, right? So both of those mean the same thing, okay? Differentiation is the operation in which we take the derivative. Okay, so and then since we're using differentiation, this is referred to as the differential branch of calculus. So this is differential calculus, which uses the applications of the derivative. All right, so we are officially in the differential calculus branch. Once we get to the antiderivative, we'll be in the integral calculus branch, okay, later on in this series. All right, so first thing we're going to do is we're going to come up with the first rule for the derivative. So again, we're not using the limit definition anymore. We're trying to look for shortcuts to do this. Okay, so keep in mind that for these shortcuts, we're going to be proving these shortcuts. But once we prove these shortcuts using the limit definition, so on and so forth, we'll be able to just use them and apply them without having to worry about the limit definition anymore. So what's the first rule? Well, first is if you have a function that's a constant. So if you have a constant function, so f of x equals like 5 or something like that, the easy way to do it is if you're doing the derivative. Well, if I use the limit definition of that, well, notice that since this function is constant, then this is going to be c, and so is this, right? It doesn't really matter if I have x plus delta x because it's a constant function. But so c minus c is 0. So the derivative of a constant function is always going to be 0. All right, so if I look at this is a constant function. This is y equals 1, y equals 2. So this constant function is f of x equals 2, otherwise, or you could just say y equals 2, same thing, right? But if I take the derivative of that, that's going to be 0. If you think about it, it makes sense, because if you take the derivative, if you find the slope of this graph, well, the slope is 0, right? The rise or run is 0. It's completely flat. Now, here's another example. If I have y equals the cube root of pi squared, remember that this is a constant, right? Pi is a constant, so the derivative of that is just going to be 0. Right? So derivative of any constant is 0. So that's the first main rule. This is theorem 9.1. The derivative of a constant c is 0. Okay, this means that you're taking the derivative of that function. So when you see this d dx, that means you're taking the derivative of c with respect to x. Okay, so that's how you read that. All right, so we're going to do the power rule. Now this one's going to be a very involved proof of the power rule, and I put proof in question marks, or quotations, sorry. This is just going to kind of show you what the rule is. Now it's very involved, so this is why I put a star on this. So you can actually skip this part of the video if you're not interested necessarily in the proof of the power rule, because the result is very simple. However, the in-between is not. So there's a lot involved in it, but you will learn a lot if you kind of follow along with the proof. There's a lot of things you'll eventually need to know. So first thing we're going to need to do is, well, if we use the limit definition, this is the limit definition just to kind of remind you. Well, then we're going to plug in x plus delta x into here. And so the heart of this proof is just to kind of show you what x plus delta x to the n power looks like. So this is the main part of what we need to do, okay? So we need to figure out what that expression is going to look like, and it's going to look relatively complex, right? You can imagine for any power n, this could, we need to figure out a pattern for how to find this. So in order to expand that part right there, you're going to need to use the binomial theorem or Pascal's triangle. So we're going to show you how to do that. We're going to show you how to use both Pascal's triangle and the binomial theorem. So let's talk about Pascal's triangle first. If you've never heard of Pascal's triangle, well, then you're going to learn that right now in this video. It's a really easy way. It's a really simple way to do binomial expansion coefficients. It has plenty of other applications, but for this video, we're going to use it for binomial expansion coefficients. So if I were to do a plus b raised to the second power, we know that's a plus b times a plus b. And of course, if we distribute, or you may have learned FOIL in your algebra class, but if you distribute, you get a squared plus 2ab plus b squared. So notice that the coefficient here is 1, the coefficient here is 2, and then the coefficient here is 1. All right, so those are things that I want you to notice. Now, if I do a plus b to the third power, well, that's the same thing as taking this guy times an extra a plus b, right? So this part right here is my a plus b squared, right, that we got from earlier. And then we multiply by another a plus b, and then that gives us the expansion a cubed plus 3a squared b, so on and so forth. But notice that the coefficients here are 1, 3, 3, 1. All right? And we'll show you maybe one or two more. So this is a plus b to the fourth power, so you're going to take a plus b to the third power, and you're going to multiply it by another a plus b. All right? So we get coefficient of 1, then 4, then 6, then 4, then 1. There's patterns to these numbers, which is why we're pointing them out. So here's the pattern. So if I had a plus b to the 0 power, anything to the 0 power is 1, right? And an a plus b to the first power, we know, so we know that this is 1. We know that a plus b to the first power is just a plus b with coefficients of 1 and 1, okay? Hence why we have the 1, 1, 1 pattern so far. A plus b to the second power, we said that this was a squared plus 2ab plus b squared, so that gives us the 1, 2, 1 pattern. So that's how we get that. A plus b to the third power, this is the pattern here, 1, you know, the 1, 3, 3, 1 pattern, so on and so forth. So a plus b to the fourth power, we have 1, 4, 6, 4, 1 pattern. Now, if you were to do this without expanding it, it's really simple. You know that this we have a wall of ones here. We have a wall of ones here, right? So this next row is going to be another wall of ones, another 1 on each side. There's always a 1 in the beginning and in the end. And to get the numbers in between, we add the numbers here. So 1 plus 1 gives us 2. We got 1 plus 2 is 3. We have 3, 2 plus 1 is 3, and that's how we get that. Then we got here 1 plus 3 is 4, 3 plus 3 is 6, and then 3 plus 1 is 4. So that's how we get the numbers in between. So here we got 1 plus 4 is 5. So we got a 5 here. We got 4 plus 6 is 10. We got 6 plus 4 is 10. We got 4 plus 1 is 5. So if we continue this with a plus b to the fifth power, we're going to get those numbers. So let me erase this. Like I said, this is the pattern that we said here. 1 plus 4, 4 plus 6, 6 plus 4, and then 4 plus 1. All right, and then notice that when you're expanding, that the power starts with the highest power, right? And a, and then a decreases in power. So 4, 3, 2, 1, and then this is a to the 0 power technically. The power of b starts at 0, so this is b to the 0, and then it goes to b to the first, and then a b to the second, and then b to the third, and b to the fourth. So you all see the pattern there? So that's always been the case. So here we got, again, b to the 0, b to the 1, b to the 2, b to the 3, while a starts at 3, a to the second, a to the first, and then here there's an invisible a to the 0. All right, so the a power decreases while the b power increases. That's the pattern that I need you to notice for that, okay? So, we're going to show you another way to calculate the coefficients. So the coefficients here that we said, the 1, 2, 1, the 1, 3, 3, 1, we're going to show you how to calculate those coefficients using the following formula, okay? So first off, you need to know how to do a factorial. So n factorial is n times n minus 1 times n minus 2 all the way to 3 times 2 times 1. So basically you decrease the number by 1 and you keep multiplying it. So for example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, right? We go all the way to 1. We do that, we get 720. All right, 1 factorial is 1 and 0 factorial is 1. So just keep that in mind. 0 factorial is not 0, okay? Because the last number when we do the factorial always has to be 1. So if we do 0 factorial, it's still going to be 1, right? And there's reasons for 0 factorial to be 1, but you don't need to worry too much about it right now. Just know that 1 factorial is 1, and so is 0 factorial. All right, here we go. And we got another formula, which is known as n choose x, otherwise known as a combination, okay? So n choose x is n factorial over x factorial times n minus x factorial. So for example, if I had 3 choose 2, this is 3 factorial over 2 factorial times 3 minus 2 factorial, all right? So here's another example right here. So if I had 6 choose 5, we have 6 factorial over 5 factorial times 6 minus 5 factorial. We know that 1 factorial is 1, right? So that turns into 1. That really doesn't do anything. And then we know that, and then 5 factorial is 5 times 4 times 3 times 2 times 1, so on and so forth. But here's a trick. We know that 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, right? So what we can do is we can call this 5 factorial and just say that this is just 6 times 5 factorial. And the reason why we do that is because now we can cancel the 5 factorials top and bottom, and that leaves us with 6. Okay, so that's a quick little trick in order to calculate these combinations. But you don't have to use that trick. It's just a way to make the calculation simpler. All right, so that's how you calculate those. Now, what does this have to do with Pascal's triangle? We're going to show you now. So in order to calculate those coefficients in Pascal's triangle, we can, for example, so when you look into this first row, this is actually the 0th row. So this is the 0th power. So the 0th power, essentially the 0th row, right? And this is the first power. So this is like the first power slash row. I guess you can think of it as that as the first row. The top one has the 0th row, right? I know it's weird saying it, but 0th row because of 0th power. And then you can think of the first number as sort of like the 0th column. So like this is the 0th column. This is the first column, so on and so forth. Or we can just say, if you want, you can call it the 0th number and the first number. All right. So this is the 0th, this is the first, and this is the second, right? And so on and so forth. And these are the numbers that you're going to use in this combination. All right. So here is going to be 0, choose 0 because this is the 0th number in the 0th row. Okay, so we got 0, choose 0, but we know that 0 factorial is just 1, so this is going to be 1, hence why we get the number 1. All right. If we do this bold one, well, that's going to be the first row, the first number in the first row, right? So that's going to be 1, choose 1. This top number right here is the row, okay, and then this is the number. All right, so that's what that is, okay? So 1 factorial over 1 factorial, this is just going to be 1, right? Because 1 factorial is 1. Now, if I look at this number right here, that is the first number in the second row. Okay, so we got 2, choose 1. Second row, you're looking at the first number, and so notice that you get 2 factorial on the top, which is 2. This is the third number, or the second number rather, because remember this is this right here. If I look at this is the 0th, first, second number, and then this is the third number right here, the number 1 here. We have the second number in the third row, so it's 3, choose 2. So we have 3 factorial is 6, and then 2 factorial is 2. So 6 divided by 2 is 3. This is how we get these numbers, okay? So I'll show you these again just to kind of so you can kind of see. But that's how you do that. That's how you can use that formula to calculate the binomial coefficients. Now this is going to help because now we can come up with a formula to come up with the expansion, right? So again, just to kind of reiterate, we have a plus b to the second power, which is a squared plus 2ab plus b squared. And like we said, we can calculate these coefficients using the formula that we said. Remember, so this is the a plus b to the second power is this row right here of the Pascal's triangle. And remember, to get this here, we got to do the second row and then the 0th number, okay? And then for this one, this is the second row, the first number. This is the second row and the second number. So that's how we get those coefficients right here, here, and here, right? So this is what we're talking about. All right, a plus b to the third power. Again, using the same idea. The coefficients here are 1, 3, 3, 1, and we can get that from these those coefficients there, okay? Also, keep in mind that we have a to the second power, and then a to the first power, and then a to the 0th power. The powers are decreasing, right? Whereas here we got b to the 0 power, then b to the first power, then b to the second power. The powers of b are increasing. All right, so we're noticing that pattern throughout. All right, and so we can come up with a generic pattern for a plus b to the n, which is exactly what we wanted to do, right? The 3, notice that it matches up the power, right? And this 2 matches up with this power right here. So then this n is going to match up with this power, right? So we have n choose 0, a to the n, plus n choose 1, a to the n minus 1, b to the first, plus n choose 2 times a to the n minus 2 power, b squared, and so on and so forth. All right, so this is our generic formula, and we know that this is 0. Sorry, I didn't mean to zoom in that far, but we know that this is 0, a to the 0 power. A to the 0 power is just 1, so this actually just turned into 1, right? So we're gonna so this is the general formula for this, but we're going to simplify this a little bit, and we're going to show you another way to do this too. Or we're going to simplify this a little more, and we're going to show you another way to write this. Okay, so here's another way to write this. This is known as the binomial theorem. So using the template that we have here, this pattern, we can write this as a summation, right? This is the Greek letter capital sigma, and this means sum, right? So this means to sum. You might have seen this in Algebra 2 if you did some series, right? Arithmetic series, geometric series. If not, then no biggie. Just know that this that means sum. And so the way this works is that you're going to start the sum from k equals 0 all the way to k equals n. So k is going to be increasing. So the first thing, k is going to be 0, and then it's going to increase to 1, and so on and so forth. So here, for example, the first term is n choose 0. You're going to plug in 0 into k there. We got a to the n minus 0 because k is 0, right? And k is 0 here. Get b to the 0. Plus, now you're going to do the sum, plus, and now you're going to increase k by 1. So now it's going to be n choose 1, a to the n minus 1, b to the 1, plus, now you're going to increase n by 2, or n to the number 2. And you keep doing this, dot, dot, dot. You keep doing this up until n becomes, or 0, and k becomes n. So then where you have n, choose n, a to the n minus n, b to the n. All right, but notice that these are the coefficients that we have here, right? So this is this guy, and then this is this guy. So it's the same expansion, all right? It's just another way to write it, okay? So that's known as the binomial theorem. That's something that I want to show you. We're not necessarily going to use that too much right now, but it's just something that I want you to be aware. Okay, so, but we're going to do this in terms of x plus delta x. Remember our limit definition? It has x and delta x in it. Instead of using a and b, we're going to just use this right here, where this is a and then this is b. A is x and b is delta x. But there's that formula. But we can expand it, right? And we get this expansion. So this is where we're going to be taking the power rule. So we're going to be using this and applying it to the power rule. Okay, let's clean things up a little bit. We know that n choose 0 is 1. How do you know that? Well, let's do that over here. So we know that n choose 0 is n factorial over 0 factorial times n minus 0 factorial, right? And n, so we can just write this as n factorial. We know that 0 factorial is 1, if you remember. And we got n minus 0 is n, so we got n factorial. But n factorial over n factorial is 1. Hence why this becomes 1. And therefore, that's why there's an invisible 1 there. Remember, delta x to the 0 is 1, so this goes away. So there's no x to the 0, delta x to the 0 term. All right, we're going to show you a couple more of these. So we'll show you, let's next do n choose 1. So if I were to do n choose 1, this can be n factorial over 1 factorial times n minus 1 factorial. Well, 1 factorial is just 1, so we can ignore that. Now, we can write this n factorial as n. So I'm going to write this as n times n minus 1 factorial. So I'm going to write n factorial as n times n minus 1 factorial. Remember what we said earlier, that 6 factorial can be written as 6 times 5 factorial. Because 5 factorial just is going to be 5 times 4 times 3 times 2 times 1, but we can stop it there. Now, why do we want to stop it there? Is because we want to cancel it out with the n minus 1 factorial down here. And that gives me n. Well, that's how we got the n right here. See, notice that this turned into n. Okay, so hopefully that makes sense. Let's do one more. Let's do n choose 2 to see what that turns into. So that n choose 2. So we got n choose 2 is n factorial over 2 factorial times n minus 2 factorial. 2 factorial is 2, right? So this really turns into 2 because 2 times 1. We can leave this as n minus 2 factorial. And I'm going to write the n factorial as n times n minus 1 times n minus 2 factorial. We're going to stop it there so that we can cancel. All right, so that gives us n times n minus 1 over 2, which this is what we have right here, right? Well, part of it anyways. We continue with this on and showing my work, we do get the n times n minus 1 over 2, all right, which is what I was trying to show you. All right, this is the clean form of it, the cleanest form you can get of, this polynomial expansion. So we're going to use this in our proof, okay? All right, so again, it's kind of showing you this is the f of x equals x to the n. We want to take the derivative of this, right? So we do the derivative rule. We have x plus delta x to the n, and we want to replace that with what we just wrote in the previous slide, all of this stuff. There you go. So all of that work was for this, so that we can replace it. And now we notice that x to the n cancels. And we notice that we can actually cancel out one of these delta x's. So we're going to pull out one of these delta x's from here, because each of these has 1. So we're going to pull a delta x out. And then this cancels, right? And so next we're going to put the limit as delta x approaches 0. So we're going to replace that with a 0. We're going to replace that with a 0 as well. Okay, so that's what we do that here. We replace this with a 0. That means all of these terms have 0. So that means this goes to 0. So it is all this. And that leaves us with, you might have guessed it, nx to the n minus 1. So this is the power rule, all right? And that's what all this was for, is to show you the power rule. All right, so here it is, theorem 9.2, the power rule. The derivative of a function, of a power function, I guess you can call it power function, x to the n, that's what I mean by that. Something raised to the n power, where n is a rational number. That means it could be a fraction, it could be an integer, it could be, negative, positive, 0, all those. All you got to do is bring the power down and then subtract 1 from the power. That's how you do it. So here, let's give you an example. Let me give you an example of this right here. So if I had the derivative with respect to x of x to the 5th power, well, then I'm going to bring the 5 power down, subtract 1 from it. So it's going to be 5x to the 4th. That's it. Really, really simple. And I know we did a lot to prove that, but we're not going to need to do that anymore. So here we go, differentiate the given function. So y equals x. Well, remember, this is x to the 1st power. So if you use the power rule, you're really just bringing the 1 down and then subtracting 1 from the power. So it's going to be x to the 0 power. Anything to the 0 power is 1. Now remember, you're going to have to rewrite this as x to the 1/2 power, because that's a radical, right? So we need to write that as a fractional power. Remember that if you have a radical, for example, the mth root of x to the n, so let me write this a little bit better. I guess we can call it the nth root. So let's call it the nth root of x to the m power. This is x to the power over index, okay? Remember, this is the power, and then this is the index, right? So it's power over index, so x to the m over n. So that's how you write the radicals, okay? So then when you use when you rewrite the radical as an exponent, then you can bring the exponent down using the power rule, and then subtract 1, okay? You subtract 1 from a half, that's negative 1/2 power. Remember, a negative exponent can be brought down. So we have 2x to the 1/2 power, and then we rewrite it as square root of x. All right, remember, this can be written as x to the negative 3 power, and then you can use the power rule to bring it down. That's exactly what we do in part C. Bring the negative 3 down, subtract 1 from the power, and then because this is a negative power, we can bring it down, okay? And since it's on top, you want to bring it down to the bottom. All right, and then we have this is a negative power and a fractional power, right? Because it's on the bottom. If I bring it to the top, it becomes negative, and then use the fraction power over index rule. And we can bring this down and use the power rule. Bring this down, subtract 1. All right, now when I do that, I get x to the negative 5/3, so that I can bring this down to the bottom, right? And that becomes a positive power now. Now what I do is I'm going to simplify this, because I don't like to have improper fractions for my exponent. And so what I'm going to do is I'm going to simplify that. So that 5/3 turns into 3/3 and then 2/3, right? 3/3 plus 2/3. So then the 3/3 here becomes x to the 1 power, right? This is 1. And then the 2/3 becomes x, the cube root of x to the 2nd. That's how we got that. All right, so it just makes it look cleaner. So practice the power rule, and practice also manipulating powers, radicals, negative exponents, that sort of thing. So here, so example 2, find the equation of the tangent line at x equals -1 of the function y equals 1 over x. All right, so remember this is the equation of the tangent line. So equation of tangent line. This is the equation of any line, right? But if we're talking about the tangent line, this m is the derivative, right? The slope of the tangent line is the derivative. Okay, so we notice that this can be rewritten as x to the negative 1. Then we can take the derivative by using the power rule. So bring down the negative 1 power, of course, and then subtract 1 from the power. That gives us negative x to the negative 2. Now this is a negative power, so I can bring this down to the bottom. Okay, so we get negative 1 over x squared. All right, so here we go. So then we're going to take the derivative, we have the derivative here, so we're going to plug a negative 1 into that derivative, right? So we get negative 1 over negative 1 squared, which is negative 1. Next, we're going to figure out what the function value is at negative 1. So we're going to plug negative 1 into this original function. But if I do that, I get negative 1 as well. So far we have that the coordinates are negative 1, and that we got that the derivative at negative 1 is negative 1. So we got negative 1s everywhere. And then we can plug that into the equation of the tangent line. So again, this is y1, this is x1, this is f prime of x1, f prime of negative 1, I guess you can say. So we can plug all that in to the equation of the tangent line. And then we're going to distribute the negative. And then we're going to subtract 1 on both sides. That gives us y equals negative x minus 2. This is the equation of my tangent line. And we're going to graph this function to show you how it looks like, okay? So if I graph this function, let me erase all this part here. The graph of 1 over x is this light blue, and this dark blue / purple, this line is the tangent line, okay? And then this is x equals negative 1. So this is the point, the tangent line at x equals negative 1, where it touches it at one spot. All right, you can tell that this is negative x minus 2 because this is negative 1, this is negative 2. So this is actually the y-intercept is negative 2, and then we can see that the slope of this line is negative 1. So here, that's negative 1, 1. That's the slope of that tangent line. So that agrees with what we got for the tangent line equation. All right, so let's look at another rule. So this is the constant multiple rule, okay? So this is theorem 9.3. So this says that if you have a function of x being multiplied by a constant, you can actually pull the constant out, right? So you can actually pull it out. And so this turns into c dx, c times the derivative with respect to x of f of x. But then this here is just the f prime of x, right? So this here turns into f prime of x. And so you get c times f prime of x. So you just take the derivative and then multiply by c on the outside. Okay? Now if I combine this with the power rule, we know that the power rule here, this is the power rule, is nx to the n minus 1, right? That's when you bring the power down and subtract 1. But then we can pull the constant on the outside, so that's what we do here. And then, so we end up getting this as the combination power rule. All right, so basically if you have a constant on the outside, just ignore it, multiply it back at the very end, and just focus on the derivative of the main part of the function. Now, if you're doing a sum or a difference, right, if you're adding or subtracting two functions together that are differentiable, then when you take the derivative, that is going to be differentiable as well. And you could take the derivative separately. So you could take the derivative of the two functions separately and then add or subtract them. Okay, that's what it's saying here. This does not work with multiplication. So you can't multiply or divide two functions and then do the derivative separately like this. You have to use a different rule, which we'll talk about later. Probably either this lesson or next one. We'll talk about it at some point, product and quotient rules. But for now, when you have a sum or a difference, you can actually take the derivative separately and then add or subtract them. All right, so here we go. So differentiate the following functions. So again, we have a sum or difference, so we can actually do them separately, okay? And then take the derivative. All right, so for the first one, this is a 1/2 right here, 1/2 as a coefficient. So we can actually, that's like our c. We can actually pull that out and do the derivative separately. We know the derivative of a constant is 0, so that's going to become 0. Now this is 1/5, so that's like our other constant. So we just pulled that out as a constant here. And we brought this up So we can write it as x to the negative 1 power, and then we could use the power rule. Okay, so now using the power rule here, we can just bring the 2 down and then subtract 1, and that gives us 2x. But then we can multiply that by the 1/2 that we just kind of ignored until now. And then here, the derivative of a constant -4 is 0. And then here we could just use the power rule, right? So that's exactly what we do, and then subtract 1 from the power. But then that becomes -2, which we bring it down as a bottom x squared, okay? And this became 1. The 1/2 times 2 is 1. All right, so this is what we end up getting. For part B, we can actually split this up into 3 fractions, okay? So we can split up into this fraction, and this fraction. That's what we're gonna do. We're gonna split up into those fractions. So if I split up into this first fraction, that's going to be 3x because one of these cancels, right? If I split it up into this fraction, then these cancel, leaving me with -1, right? Then lastly, if I split it into this fraction, that's going to be 1 over x. That's how I get that. I can use the power rule. This is invisible 1 power, so I can bring the 1 down, subtract 1 from the power. Bring this up as an x to the -1, and then use the power rule, okay? So if I do the derivative, then this is going to become 3x to the 0 power, right? But x to the 0 power is 1. Then this constant became 0 when I take the derivative of constant 0. And then if I subtract 1 from this power, that's -2. So that's how I got the -2, but I brought that down as a second power. So I got this -2, which I brought down. All right, so hopefully that makes sense. And in part C, this is 3/2. So we pull that 3/2 off to the side. That's like our C, right? So we kind of ignore that, just put it off to the side. And then this here became x to the -5/3 power because it's on the bottom, so we want to bring it to the top, so it becomes negative. And then we have the power over index rule. Okay, so then that's what we get. And we take the derivative of that. So then we're going to bring the this -5/3 power. See if I can, there you go. So we bring this -5/3 power into the front and then subtract 1 from it. And if I do that, I get -8/3. That's what I get when I subtract 1. Because subtracting 1 from this is the same thing as subtracting 3/3. Sorry, I didn't mean to zoom in that far. So I'm gonna see if I can go back. Okay. Subtract 3/3 from it is the same thing as subtracting 1. So that's how I get -8/3. All right, and then I can bring this power down because it's a negative power to make it positive. And remember, this is 8/3, so I'm going to split up 8/3 into 6/3 plus 2/3, which is exactly what I do here. But 6/3 is just 2, right? So this becomes x to the second. And then the 2/3, remember the 2/3, you have to write it as a radical cube root of x to the second power. All right, and then the 2x, this is an invisible 1, so bring the power down, and then subtract 1 from the power. So that just becomes -2. Okay, so hopefully that makes sense. I know there's a lot of there's all different parts to it, but overall, it's just a bunch of power rules. Okay, so if you want to skip this proof of the derivative of sine, please feel free to do so, but I'm going to show the proof for sine and cosine. The derivative of sine and cosine is very simple, but just we just want to show you the proof, just to kind of show you why it is the way it is, all right? So if you're interested, follow along. Otherwise, you could skip to the actual derivative. So here's the definition of the derivative, as you may recall. And then we're going to plug in x plus delta x in here for sine, right? So we get sine of x plus delta x minus sine of x over delta x. And so we have to figure out what this is, right? Of course, that's the hardest part of the proof, is just trying to figure out what that is. But it's not too bad here. You have to remember the identity for the sum of two angles identity, right? The sum identity for sine and cosine. But this one's for sine. So sine of a plus b is sine of a cosine b plus sine of b cosine a. So again, we can use x and delta x here. We don't have to use a or b. This is just a generic rule. So it's going to be sine of x delta x cosine of delta x plus sine of delta x cosine of x. So that's what it's going to turn into. So this is what we get using that identity. Again, this is the sine of x plus delta x part. But then we can move things around a little bit, just rearrange things a little bit. So what I'm going to do is I'm going to just move this to position 1. Then I'm going to move this to position 2. And then this is to position 3, okay? And then in here I'm gonna pull out a sine of x because this has a sine of x in common, so I'm gonna pull that sine of x out. So that's why I get this, okay? That's how I get that. And then what the reason why I'm doing that is because now I'm going to split this up, sine of delta x over delta x, and then I'm going to split this up right here, 1 minus cosine over delta x. And then I'm going to distribute this limit to both of these because you can distribute the limit if you have a sum or a difference. And then remember that if I do the limit of this turns into 1. The limit of that is 1. This was in one of the previous lessons about limits involving trig functions, right? So the rule is limit of as x approaches 0, a sine of x over x is 1. And then the limit as x approaches 0 of 1 minus cosine x over x is 0. So this actually turns into 0. Okay, so pretty neat. And then when we do that, this is going to go away. So the derivative is cosine. So the derivative of sine of x is cosine. So interestingly enough. Now we're going to do the derivative of cosine. Again, you can skip this if you want and go straight to the result. But this is going to be cosine of x plus delta x. This is the part that we got to deal with, of course. Using the identity for cosine of a plus b, we can say this is x and delta x if you want. So that way we can easily plug it in. And then this is x, delta x. All right, so this is what we get. This is the expansion part. All right, and then we're going to just rearrange things a little bit. So I'm going to put this in the first position right here. I'm just going to move this to the second position and this to the third position. Okay, so this is the second, this is the third. Now then we pulled out the cosine from here and from here, right? And that's how we got this part right here. And then we're going to split this up into this sine delta x over delta x, and then this 1 minus cosine over delta x. And similar to before, we're going to split the limit. And we know that the limit here becomes 1, the limit here becomes 0. So this goes away. So our limit is negative sine of x. So the derivative of cosine is negative sine. All right, there's the proof, but here is the result, okay? So if you skip to this part, that's perfectly fine. The derivative of sine is cosine. The derivative of cosine is negative sine. I personally like to know where the formulas come from, but if you just want to memorize the result, that's fine too. I like to understand why, because by understanding why, it actually helps me remember the formula better, because I actually understand how to get it. So either way, to each their own. But here's the result. The derivative of sine is cosine. Derivative of cosine is negative sine. All right, so here goes. So example 4, differentiate the following functions. So we got f of x equals sine of x over 3. Remember, this is an invisible 1 here, so this is actually 1/3. So you can actually pull that out. So we're going to pull that out as a 1/3. Then focus on taking the derivative of sine. But the derivative of sine is cosine, so it's just 1/3 cosine. That's it, done. Now part B is sort of a cheat, it's sort of a trick. So I'm going to put a star by it. It's not necessarily one where you would take the derivative. So you can't take the derivative of this directly in this lesson at this point in time. Once we get to chain rule and that kind of stuff, then we will be able to do this derivative directly. So we're going to do this derivative indirectly. So we're going to use an identity, the double angle identity for cosine, which is cosine of 2a equals cosine squared a minus sine squared a. All right, so in other words, this angle is exactly 1/2 of this angle, okay? So for example, in this example, because we have cosine squared of x over 2, then that means this is my a, which means that 2a is 2 times that. But guess what? 2 times the 2's cancel, so we get cosine of x is equal to cosine squared minus sine squared. That's exactly what we got here, right? That's exactly what we're going to do. So this actually turns into cosine of x. And then you can take the derivative of cosine of x. It's a pretty interesting trick, right? But like I said, if you don't know this trick, it's not a big deal, which is why I put a star on it. It's just something that I thought I'd share with you. I will be able to do derivatives of this directly in a future lesson. But, for now, we're going to need to use some tricks. So here's the trick. So you get the derivative of that is, or the function is equal to cosine. The derivative of cosine is negative sine. So there's our derivative. Now the second one, we know the derivative of cosine is negative sine. Now this is a constant. So the derivative of a constant is 0. So don't get tricked by that, right? So don't say that it's a cosine of pi. So that's not going to make sense. Sine of pi is a number. The derivative of a number is 0. Okay, and then the derivative of sine here is cosine. All right, remember this is just a constant that we pull out off to the side. So those are the derivatives. So we're gonna do the last part of the lesson by talking about rates of change. So remember that the delta y over delta x is the average rate of change, okay? And the dy dx is the instantaneous rate of change, okay? So because we're talking about rate of change, this naturally applies to physics when we're talking about velocity, right? So if we're trying to find the velocity, average velocity of an object or an instantaneous velocity, naturally this uses the language of calculus, right? So instantaneous speed, instantaneous velocity, derivative, that kind of stuff. So the slope of the tangent line dy dx can be used to find the instantaneous rate of change. So it's used for the instantaneous velocity. So remember, instantaneous velocity is the velocity that if you're driving a car at a specific moment in time, you look at the odometer, that tells you the speed, right? So if you look at the speed and it says 60 miles per hour, that's your instantaneous velocity, right? At that specific point in time, your velocity is 60 miles per hour. Now the average velocity is when you average out the different speeds over a trip, right? Over a specific time interval, right? So that's the average velocity. So for example, if I started going really slow and then later I went really fast and then later on I went really slow, I averaged those velocities and that gives me an average velocity, right? But if I'm talking about a specific moment in time, well, at this stoplight, I went 0 miles per hour. That's my instantaneous because I stopped at a stoplight. And then later on the highway, I went 60 miles per hour. That's instantaneous, right? So delta y over delta x is the average rate of change over a specific time interval. Dy dx is instantaneous time rate of change function, right? So notice that this is a value. This is generally a function. And if you plug in a value into it, then you get a number, right? So distance over time is velocity, right? So average over the average velocity over a specific time period. Dx dt is the instantaneous velocity. You can have dy dt as well. Y could be the speed. Y could be the distance. If you're going up and down, we traditionally call that y, right? If you go left to right, we traditionally call that x. So you could have dy dt. It doesn't have to be dx dt. Okay, it could be any variable that you want to use for distance. And then dy dx is the instantaneous rate of change at x equals c. So this is like this symbol right here with this x equals c means you're plugging in this into the derivative, right? To get a specific value. And then this here is the instantaneous velocity at a specific time period, or a specific time. So let's go ahead and use these two concepts for the following problem. So this one's a physics problem, right? So a ball is thrown up from a height of 80 feet with an initial velocity of 10 feet per second. The ball's height at time t is the position function given. So it says y and y sub 0 is the final and initial heights. G is the acceleration due to gravity. Okay, we have gravity here, it makes sense. And the constant for gravity is 32 feet per second per second. And then v sub 0 is the initial instantaneous velocity. And then t is the time. And the time is going to be in seconds because this is in seconds here. All right, so we have the initial velocity of 10 feet per second. So we're going to actually plug that in here. We have the g, so we're going to actually plug that into there. And then we have y sub 0 because it says we have this is thrown up for 80 feet. So that's actually our y sub 0, right? So we're actually going to plug that in there. Okay, so let's do the first part. Find the average velocity of the ball over the time interval from 1 to 1.5 seconds. Let's do that part first. Let's find our position functions. Remember, we said we're going to plug G32 in for there. We're going to plug in 10 into that, and then 80 in for that. So that's how we get that. Half of 32 is 16. Okay, so that's our position function. We're going to need to find the average velocity. So remember, the average velocity is here going to be change in y over change in t. We're using y because this is our position function is y. Okay, so change in y over change in t. And then we got y of 1.5 minus y of 1. Those are these two times. So we're going to subtract it at 1.5 seconds, and then subtract that minus the y at 1 second, and then divided by the time period from 1.5 to from 1 to 1.5 seconds to subtract that. Okay, that's our average velocity. So we need to find y of 1.5. So plugging in 1.5 into that position function here, right, for t gives us 59 feet. Then we're going to figure out what y of 1 is, plugging it into the position function, so we get 74 feet. So at 1 second, it starts out at 74 feet, and then at 1.5 seconds, it's at 59 feet. So initially, at 1 second, it started off high, and then in 2 seconds, it started off lower than where it was before, right? So I guess here it was 74, and then here is 59 feet, something like that. Oh, not 2 seconds, 1.5 seconds, all right? And then we're finding the average velocity, plugging into that function. So we have 59 minus 74 over 0.5. So that gives us an average velocity of negative 30 feet per second. All right. So now let's go ahead. So this is our average velocity over that time period. So now let's look at when does the ball hit the ground. So this is a parabola. If you notice that this is a quadratic function, right? Highest power is 2. So we know it's going to be a parabola. So it's going to go like this. It's going to be going down because it's negative. Negative parabola goes down. So we are going to have a maximum height, and then we're going to have a point where it hits the ground, right? So when does the ball hit the ground? So we're going to set this position function equal to 0, because when it's 0, it's going to be hitting the ground, right? 0 means the height is 0, which means it's at the ground. So we're going to set equal to 0 and solve it. Let's divide everything here by 2, because they all go into 2, or 2 goes into those numbers. So let's just make the function simpler, and this is what we get when we divide by 2. Then remember, we have to either factor this or use the quadratic formula. We cannot factor this. This is a prime polynomial, so we're going to need to use the quadratic formula. Remember, the quadratic formula is negative b plus or minus square root b squared minus 4ac, all divided by 2a. All right, so we're going to solve this using the quadratic formula. This is a, this is b, this is c. All right, plugging it into that, we get 2 times negative 1.95 seconds and 2.57 seconds. Obviously, we're going to ignore the negative time because it's nonsensical in this application here anyways. So we get 2.57 seconds. That's when it's going to hit the ground. So now we know when it hits the ground. So now that we know it hits the ground, it says what happens when it impacts the ground? What is its velocity? Well, we just said that it's 2.57 seconds, right? Is when it hits the ground. So we're going to find the instantaneous velocity, which means derivative, right? So we're going to do the derivative. We're going to do dy dt. So basically, we're going to do the derivative of this function, right? We're going to do it with respect to time because the variable here is time, right? So we're taking the derivative with respect to time. And so that's dy dt. So dy dt over y prime, same thing. We're going to use the power rule. So now this is when we use the power rule. Bring down the 2, subtract 1 from the power. Bring down this invisible 1, subtract 1 from the power. The derivative of a constant is 0, right? So that's what we get. So let me multiply these to get negative 32. This is going to be 10. So our derivative is simply negative 32t plus 10. That's our instantaneous velocity function. Then we're going to plug in the value here to find the specific derivative at that time. So 2.57 seconds, plug that in, and you get a instantaneous velocity of negative 72.24 feet per second. So we had an average velocity over a small period of time, and we have a specific velocity at a instantaneous velocity at a specific time. So there's a difference between those two for sure. All right, so that's going to do it for the lesson, guys. I hope you found this useful and informative. Found some shortcuts for the derivative. And as usual, I'll see you in the next one.